This is Unit 3, Video 12, and in this video we will wrap up talking about the intermolecular forces. Now, last time we discussed three intermolecular forces: London dispersion, dipole-dipole, and hydrogen bonding. Now, this graph, or this table, arranges them in order of increasing, up here, strength. So, the weakest of the forces are actually London dispersion forces. The strongest of the forces are the hydrogen bonding, and we mentioned that last time. Now, we also include covalent bonds. These are chemical bonds between the molecule, within the molecule. This is a chemical bond. So, for example, these are your single, double, and triple bonds within a molecule, say between carbons. And then all the way up here you have ionic bonds. Ionic bonds are actually the strongest because you have a full positive and a full negative operating. So here we have examples, and here also we have strength, typical energy strength. So these are kilocalories per mole, so you can see the numbers that correspond to it. Now, we looked at ionic and covalent bonds at the very beginning of the chapter, and it's important to realize that these indeed are chemical bonds. The attractive forces that we looked at all the way at the beginning are chemical bonds, whereas these attractive forces are actually physical bonds, and you have to keep that separate. All of them require energy to break, but the physical bonds are much, much weaker. In fact, notice, anywhere from 2 to 10 versus these are usually above 100, and they go into the thousands. Some of the lattice energies, for example, could be a few thousand in their size or strength. So these three, you have to realize that these three down here that we'll be discussing are physical bonds due to the bonds between molecules, whereas these up here are chemical bonds due to the bonds within a molecule. So really two different stories. We're going to keep focusing on these down here as we wrap up the chapter. And so let's talk about these in a little more detail. So boiling point is one of the ways that we can check that a substance has weaker or stronger intermolecular forces. So there are two factors we usually consider when we're discussing boiling points. Number one, that's the nature of the intermolecular attraction. Well, nature and strength, which means which type of intermolecular attraction do we have? Is it dipole-dipole? Or is it London dispersion? Dipole-dipole would be the stronger one. And then the strength, because dipole-dipole varies in strength. So one molecule can have a stronger dipole-dipole force, another can have a weaker dipole-dipole force, and same thing with London dispersion. And then the second factor we consider is the molecular size and shape. Now, molecular size will actually have a very big effect, as you'll see, on how strong the dispersion forces are. And then we'll talk about shape as well and how that affects it. So here you have just a bunch of molecules, and along with that, they're boiling points. Now, these boiling points actually correspond to the strength of the intermolecular forces. So the higher the boiling point, for example, this substance down here has the highest boiling point, which is acetic acid, and it has the strongest forces between its molecules. Water is actually not too far off. And water has a pretty strong force as compared to other similar molecules, is the idea. Alright, so we'll take a look at boiling point first. So consider CH4. Now CH4, here it says molecular weight of 16, so we simply calculated carbon plus 4 hydrogens. Has a really, really low boiling point. In fact, methane is a gas, and it's really tough to liquefy it. It'll be a gas well below room temperature. Whereas water's molecular weight is 18, so that's about comparable to methane. We're trying to compare molecular size because molecular size will have a big effect on the forces. Notice they're about the same. However, water's boiling point is well above room temperature at 100 degrees Celsius. The difference here is because there are much greater strength of hydrogen bonding between water molecules compared to only London dispersion forces between methane molecules. So this is actually methane, this is CH4, and this is water, H2O. Notice they're about the same size. However, water is a liquid, whereas methane is a gas. Again, water not only is polar, but it has hydrogen bonding. It's extremely, extremely polar, and it has H bonding, and that's what creates that difference. And this is nonpolar, and only has London dispersion forces in it. Okay? Now, what if we consider methane and consider this molecule right here, which is something called hexane. Now, the boiling point of methane is obviously well below room temperature, but hexane's boiling point is above room temperature. Notice 69 degrees Celsius. Now, if you take a look, hexane has a molecular weight of 86, quite a bit higher than methane's 16. So in this case, what you have, now both of them are nonpolar. If you take a look, they're both evenly distributed, and actually because they're both hydrocarbons, there's really no difference in electronegativity, or a really small difference, about a 0.4 difference between hydrogen and carbon. So you don't have any polar bonds within the molecule, technically. So the whole molecule is nonpolar. Both these are actually nonpolar. But because hexane is such a bigger molecule, the dispersion forces are stronger, and making hexane into a liquid. And that's the idea. The idea is, if you consider just nonpolar molecules, the size makes a big difference. If you consider polar molecules, then you have to consider the fact that a polar molecule has dipole-dipole and maybe even hydrogen bonding. So this is an example of considering both the type of force and the strength of the force and the size of the molecule. Okay, now how about we consider the shape of the molecule? Here it says when the molecules are similar in every way except shape, then the more elongated molecule will have the higher boiling point because they have the strongest attractions. So here actually you have two substances that have the same molecular formula. In fact, you have 5 carbons, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. Then if you calculate the hydrogens, you'll see each of them has 12 hydrogens. So the molecular weight would be the same. However, this is called pentane. It has a boiling point of about 36 Celsius, which is above room temperature, so it's a liquid at room temperature. Whereas neopentane has a boiling point below room temperature, so this would be a gas at room temperature at 9.5 degrees Celsius. So they both have the same molecular weight, but the higher boiling point of pentane is due to the fact that the shape is longer. And actually, if you have a longer shape, you actually have a larger surface area, which means you can think of this as the electrons can disperse more. If you think of a balloon, say a balloon that you've blown up that's spherical, and a balloon that's maybe more elongated, the more elongated is easier to manipulate than the spherical one. And that's really why, because you have more surface area. So the dispersion forces can actually vary based on size and shape. Alright, so let's try to arrange these in order of increasing boiling points based on our examples. So here we have CH3Cl. Let's draw the Lewis structure, and if we do this, the carbon goes in the middle. We have a chlorine on one side and then hydrogens filling the rest of the sides of carbon, and we have a full octet on the chlorine, and the hydrogens are good. With CH3OH, this one here, you have a very similar structure. You actually have 3 hydrogens on every carbon, and then the OH is bonded like this. It's the oxygen bonded through to the hydrogen, and if you do the Lewis structure correctly, here's what you'll see. Then finally CO2, we've drawn CO2 before, should have 2 double bonds on every side of the molecule, looking like this. Okay, so right away what we realize is that CO2, remember, is nonpolar. We've seen it to be nonpolar because the 2 dipoles right here will cancel each other out, and you get yourself a nonpolar molecule. Whereas in this case, CH3Cl is actually polar because chlorine will pull the electronegativity difference toward it, so creating a slightly negative side to the molecule. And then this one's also very polar. Not only is it very polar, you actually have hydrogen bonding here. So this will actually exhibit H bonding. So this one is polar, so you have dipole-dipole forces, and everything has London dispersion forces. This one has hydrogen bonding, which means it also has dipole-dipole forces, and then everything has London dispersion forces. And this one's nonpolar, which means all it has is London dispersion forces. So if we take a look at the type of forces present in these molecules, you'll see that this guy here wins because it has the most forces between the molecules. And so this one should have the highest boiling point. So we should say this will be 3. This will be the third, because it says an order of increasing boiling point. CO2 has the least forces, so we'll say this will be lowest boiling point, and then CH3Cl will be second. And if you take a look and look up their boiling points, you'll see this is the case. Now, it's hard to know the exact boiling point, but if we arrange them in this order, we can predict with high certainty that this will be the case. So hopefully that makes sense. If we were to compare molecules that are all nonpolar look at the size of the molecule. So for example, just as a quick example, if we were to look at, say, CH4 versus CCl4 versus CI4, what you have here is you have progressively bigger and bigger molecules because iodine has more electrons. So then you would actually arrange it in this order. CH4 will have the lowest boiling point because the smallest molecule. This is next up, and this is third, because all three of these will be nonpolar in nature. So hopefully that makes sense. And we'll finish with this statement. Intermolecular forces affect many other physical properties, and things like viscosity, surface tension, heat of vaporization, even solubility, how well the molecules dissolve in one another, is due to intermolecular forces. So really important. Sometimes you call these IMFs for short. You may hear some chemists talking about IMFs, and that's what they are discussing. So we'll actually take a look at this and show you pictures like this. This is viscosity, by the way, how thick a fluid is, and this is surface tension. And there's a film on the surface of liquids that forms due to the high attraction between the molecules. All right, but we'll discuss this in a future section.